In the next 8 minutes, you'll learn a clean, repeatable way to determine whether two molecules are identical, enantiomers, or diastereomers without guessing. Hey there, ninjas. In a previous video, we learned how to count up the number of possible stereoisomers for a given molecule. In a separate video, we learned how to describe those single molecules with descriptor words, chiral, achiral, or meso. If you'd like a refresher on those concepts, I have a link in the description down below. In this video, we are comparing two molecules and asking one question. What is the relationship between these two molecules? Words like identical, enantiomer, and diastereomer are relationship words. They only make sense when two molecules are present and we're comparing them. We can't draw a single molecule and say it's identical. Identical to what? That word is meaningless without a partner. If you keep the concept of descriptor words and the concept of relationship words separate, the stereochemistry unit gets much easier to manage. Before we go too much further, let me make one disclaimer. For all of these comparisons, we're looking at two molecules that are stereoisomers of each other. That means they have the same molecular formula and the same connectivity. The only thing that differs is their three-dimensional relationship between each other. We're not talking about constitutional isomers, where they have the same molecular formula but different connectivity. That's a different video entirely. And if we're looking at molecules that have different molecular formulas completely, then they're just different molecules, and this aspect doesn't really apply. With that assumption out of the way, our definition of identical molecules, they're identical. They can be completely superimposed one on top of the other. We can take one molecule, manipulate it, rotate it, flip it, do bond rotations, but we're trying to take one molecule and make it completely identical to the other molecule. For example, for this molecule here, if I take the second molecule and I flip it like a pancake, the carbon-carbon bonding network will be the same. And when I take that dash group and flip it like a pancake, it will flip over to the wedge side of the molecule. And notice by doing that, these two molecules are now completely superimposable. I can pick this one up, put it right down on top of the other, and they are the same molecule. These molecules are identical. Don't get thrown off if they're drawn in a different orientation from the beginning. Different drawings do not necessarily mean different molecules. The next word on our list is enantiomers. The definition of enantiomers is non-superimposable mirror images. So what does that mean? We need to start with two molecules that are drawn as mirror images of each other. One molecule perfectly reflected in a mirror gives us the other molecule. One handy trick is if you place your phone between the molecules, you can see the reflection of the first molecule in your phone screen, and it needs to look like the second molecule. Sometimes molecules won't be drawn as perfect mirror images, but we can rotate and manipulate them to becoming mirror images. Being mirror images is the first part of our definition. The second part is non-superimposable mirror images. If they're going to be enantiomers, the mirror image cannot be the same as the original molecule. Right now, if we tried to pick up the first molecule and put it on the second, the chlorines on the wedge would line up, but the bromine and the methyl group would be on the wrong sides. So let's try to fix that by doing a pancake flip of the mirror image to get the carbon and the bromine on the correct orientation. If I flip the second molecule like a pancake, that will put the bromine on the right side of the molecule. And when I do a pancake flip of the wedge chlorine, it will become a dash chlorine. Now if I try and superimpose these molecules, if I pick up this version of the molecule and lay it over top, the carbon and the bromine are in the same orientation, but now the chlorines are in the wrong orientation. These molecules are mirror images, but they are not superimposable in any rotation or flip. When the relationship between two molecules is non-superimposable mirror images, these molecules are enantiomers. Enantiomer comes from the Greek words enantios, meaning opposite, and mer, meaning part. Opposite parts. We have to be careful sometimes when we look at these relationships because the molecules might not be given to us in perfect mirror image relationship pairs. We will often need to apply some combination of bond rotations or pancake flips or steering wheel rotations in order to get one molecule to be the mirror image of the first. For this top molecule, we can do a pancake flip horizontally to get this molecule to be the mirror image. When I do the pancake flip, this bond that's on the right side of the molecule will be the first bond on the left side of the molecule, and the carbon chain will continue from there. When I do the pancake flip, this dash chlorine will flip onto a wedge, and so will the other chlorine. Now these molecules are perfect mirror images of each other. The question is, are they superimposable? And the answer is no. In this first version, the left-right orientation of the carbon chain is the same, but the wedge dash version is off. In the other version, the wedge dash version of the chlorines are the same, but the carbons are off. With mirror images that are not superimposable, these molecules are another example of enantiomers. Looking at this next example, again, these are not perfect mirror images of each other. Let me do a pancake flip to see what happens. When I pancake flip this molecule, the chlorine that's on the wedge will become a chlorine on the dash, and the chlorine on a dash will become a chlorine on a wedge. That makes these molecules perfect mirror images. The question is the mirror image superimposable on the original? It certainly doesn't look like it. When the carbon chains are the same, the wedge and the dash are off. But watch one more flip. If I flip this molecule vertically like a pancake, my carbon chain starts off angled up, and the chlorine flips to a wedge on the left and a dash on the right. Now look at this last molecule compared to the first. These molecules are identical. With the right orientation switch, the chlorines and the carbons perfectly match up in each case. These mirror images are identical. What does that mean? It means we don't have a pair of molecules. We have one single molecule drawn now 4 different times. All of these other drawings are identical to the first somehow. The last molecule is identical to the first. This molecule is identical if we do that vertical pancake flip. And this molecule is identical if we do a steering wheel rotation. We bring the dash chlorine down to the right and the wedge chlorine up to the left. What does that mean? It means that these molecules are identical. And that's very sneaky because it almost looked like they were going to be enantiomers at first. We saw this concept in a previous video. This one molecule with 2 or more stereocenters is achiral and meso. This isn't a video about mesomolecules or descriptor words, so I'll refer you back to that video for more information. But I'll warn you, for the context of this video, there will almost certainly be a relationship word where 2 molecules look like enantiomers, but are really identical, and that one molecule will end up being meso. It's one of the biggest gotcha questions on an exam. How about our last example? These 2 molecules are not drawn in mirror image form. Let's flip this molecule horizontally like a pancake. That puts our carbon backbone in the correct orientation for mirror images, and it rotates the dash chlorine to a wedge, and the wedge chlorine to a dash. And that's odd because these are still not mirror images. The carbon backbones are mirror images, the dash chlorines are mirror images, but not the wedge chlorine. Let's try one other steering wheel rotation, see if we can make them mirror images. If I take this molecule and rotate it like a steering wheel, that will end up keeping the carbon backbone in the same orientation. And with the steering wheel rotation, the dash chlorine will steering wheel down to the bottom left, and the wedge chlorine will steering wheel up to the top right. Now the carbon backbones are mirrors, and the dash chlorine is a mirror, but the wedge chlorine is still not a mirror. These are still not mirror image molecules. So that's unusual. They're clearly stereoisomers. They have the same molecular formula, the same connectivity. They only differ in their 3-dimensional arrangement in space, but they're not identical, and we can't seem to rotate it into being a mirror image of the original. That, friends, is the textbook definition of diastereomers. Molecules that are stereoisomers, but not mirror images. These molecules are diastereomers, not diastereomers. Diastereomers also comes from the Greek, mer meaning part, stereo meaning 3-dimensional, and dia meaning apart. They are 3-dimensional objects that are apart from each other. We can't quite get them in the right relationship. This category is broad, and its definition is a little fuzzy, and that's okay. It's defined by exclusion. It's honestly my least favorite textbook definition for that reason. In a separate video, I'll show you some enantiomer and diastereomer tips and tricks that'll gloss over some of these confusing definitions. But it is important to know the textbook definition of these words because we will see some edge cases where the textbook definition is really the best descriptor. One final note before we close this video. Every chiral molecule can have at most 1 enantiomer, but it may have more than 1 diastereomer. If you think you found a series of 3 molecules that you think are all enantiomers of each other, that means at least one of them is mislabeled. When comparing 2 molecules on an exam, the textbook way to do so is to convert one molecule into the exact mirror image of the original. Then test for superimposability. If they are superimposable, then they'll be identical. If they're non-superimposable mirror images, they'll be enantiomers. And if they never quite become mirror images, then they are diastereomers. Don't guess, follow the order. If this felt very rigid and textbook and procedural, that was intentional. Comparing molecules is a skill, not a guess. But in the next video, I'll show you a shortcut for enantiomers and diastereomers that glosses over a lot of this textbook definition stuff. You're building this correctly, laying the proper foundation at this point. I'll see you in the next video, ninjas.
Thanks for watching. The best way you can support this channel is to let your friends know about these videos, especially ones who go to different schools. Help spread the word around the country. As always, don't forget to like and subscribe.